Hi, in this tutorial we will have a look at how we can simulate distributing land uses on plots, and the tutorial is divided into two parts. This one will explain the algorithm, and the other one will show how to customize the algorithm. And we will distribute the land uses with land use profiles, and they will define how attractive a plot is for the land use, and this is dependent on different factors. First of all, like the location of the plot within the street network, for example, or the terrain, so the slope or how central it is located, and also on relational factors. Is the plot, in what kind of distance is the plot towards other land uses that we might prefer or not, such as residential might not prefer industry close by. So within Rhino we have our streets as hierarchies here: primary, secondary, tertiary street, and also our plots already. And in Grasshopper, if I turn this on here, you see how the land use is distributed. This is the algorithm, and when you open the file it will take quite a while to calculate. So be patient, and it really depends on how many plots you have. The more you have, the longer it will take to calculate. Same for the streets. And another factor is how many iterations you want the simulation to run. I put it on a low value, and I would recommend for you to do the same, because otherwise it takes quite a while to calculate. If you want to have more precision, then you can also increase it, and then you have to wait for a while. But yeah, start with a smaller one. And if it calculates too long, you can also just break the simulation, and then I would recommend like setting the iteration lower and then run it again. Like you have to set it to false that it can run. And as you can see, it takes a while. Yes, those were 6 iterations. Okay, so let's start with the location with factors. They're actually named in this file rather contextual factors. So here we have our land use profiles, one for residential, one for commercial, one for industry, and there's a possibility to add more profiles. So the locational factors in this case are centrality and accessibility measures. Like in space syntax terms, it's like closeness and betweenness centrality. And I can define here how important this is for different functions. So industry, for example, doesn't need to be in the center, but prefers accessible streets to bring the goods out and inside of the city. Commercial also prefers well-located streets for higher frequency of pedestrians, for example, and consumers, and therefore it also it's mostly located in the center of the city. And for residential it might not be that important. Like, this is the argumentation that I made here, and the values might not be that correct, but we can see over here how this influences the evaluation of plots. So as I stated before, we can evaluate each plot for these criteria. You need to set here weighted values. Now we have the profile of industry. As you can see, it's not so attractive in the center, but more on the outskirts. Commercial prefers central locations, but also accessible locations. Yeah, and residential then avoids the other places. So yeah, these are the location factors, and they are mainly calculated in our case now in terms of centrality and accessibility. You could add slope too of the terrain, but I filtered already the plots by the slope, so I didn't include it in here. And to calculate the distances from one plot to another, we have to get in our streets here, as well as the plots, to assign first of all the according values. Like for example, because we have the hierarchy of streets, I give each street hierarchy, like primary streets are higher weight than the secondary streets or tertiary streets. So when going from A to B, they would prefer going those streets. And then for the plots, we need to calculate the plot center and the area, and we can even assign already the population per plot with the assistance of our profiles here, because I stated how much population they should each have, and then we can say how much would fit on each plot. And then we need to interrelate, like actually, because we do the street shortest path calculation on top of the street network and not on the plots, we need to find out which plot relates to which street segment. So I can even draw a line. So here you can see which plot is closest to what kind of street segment. So we can do our shortest path analysis from each plot to all others, including the weights of the streets that we have here. Then, like here, street segment per parcel plot is then our 244 locations of the plots here in the street network, and we do our shortest path analysis here, or like space index analysis, because it will do it from each of these destinations to all others. And as you can see now here, like the more plots you get, the more calculations it will need to do, and that takes quite a while. And I've included two different calculations in here. That is because the lower one gives more information, or more precise information, but takes longer to calculate, because it needs to supply this paths information, and that's quite heavy to calculate and will take I don't know, maybe 20 times the time as this one. And it needs to calculate with the CPU, which is not as fast as the GPU. Either way, the GPU you can only use when you have a suitable one on your computer. However, you can switch between the calculation methods up here: simplified direct distance, precise distance. I will explain what this means later. Okay, but we get our betweenness and closeness centrality here, and these values then are multiplied, interrelated with our weights for the contextual criteria, so these values. And this gives us, in here in the C#, it's just really weight multiplied with the values. Gives us then the evaluation that we saw here, this one. So this is the location factor. The C# is really just, I had to use it because I had to keep the branches in the same structure. It's a bit of like the data flow is really important in this whole workflow. So next up we have the relational criteria, and they are a little bit more complicated, I would say, because they are dependent on, like, later in the simulation it's more dynamic, because depending on where residential will be placed, it changes the attractivity for the industry that will be placed in the next round. But since the distances from like if residential is placed here and industry here, it doesn't matter in which iteration we will calculate this, we always know how this would influence each other. So what I will do is I will calculate all attractivities, like from each plot to all others, for each land use to all other land uses before I start on my simulation. Because if I wouldn't do this, I would have to calculate it each iteration, and that takes a lot of time. And that you see here, because this is, so here's our iteration happening, that runs like currently 6 times, but if you set it to 50 it would take ages, especially if you would include this part. Like this is, as you see here, showing us from each plot to all others, from each profile to all others, the attractivity, and that takes already half a minute. So if you add more plots, if you add more profiles, it will take longer and longer to calculate. There might be more efficient ways of doing this, but currently I thought it is the easiest way to deal with this at this phase. So yeah, for example, like if I would choose here plot this plot here and this plot, I have in my data structure, I know like the attractivity. If residential is here, I know the attractivity, how it relates to commercial and industry on this plot, and the other way around. So when I've later on, when I'm in my iteration and I place residential somewhere, I only need to look up inside of this whole table how is the attractivity to the others. I don't need to calculate it anymore. Yes, and there's one other factor that is going into this calculation is then, yeah, so we know like the attractivity from, like for here from residential to residential, to commercial to industry. For example, here residential doesn't prefer industry, commercial prefers residential around it. These are values currently from one profile to another, but they are not spatial yet, because only when we get a distance to it, like from this point to this point, then it gets more interesting, because there's a difference if industry is, like if residential is here and industry is there, or even here, like there's a fall-off function, and that is what our perceived distance is doing. More to it later. There are different ways on different perceived distance functions, but there's like the closer it is, the more attractive or repellent it is, or and yeah, like it states if close functions are good or not. So, and this is yeah, this was here the perceived distance function, and we have the distances from one plot to all others from down here, and we just multiply it, and then we get our distance in general. And one more remark in here, that is like the distance from one point plot to all others is currently calculated with a simplified version that I stated before here. It's again a matter of like this calculation time. So one takes a few seconds, the other few minutes. Over here, so this is really just aerial distance, and this one is really shortest path distance. As stated before, this would take much longer. You can set it, you can try it out if you want at some point when you know you have time to calculate it. But currently, let's use the aerial distance here, and then yeah, as stated before, we have the perceived distance and the distances to plots. They are multiplied with all attractivity values. I think this is again a simple function here. Yes, the attractivity times the distance from one plot to another, and yeah, that would be it for the relational factors, but actually this one is really also including the locational factors, because we know already, like if residential is placed here and has a relation to all the others, we also know, like as you see here in the grayscale image, it's locational preference. So we just multiply it with it. It's that simple. And then we have the attractivity value for a specific profile on a specific plot in relation to all other plots and profiles. Quite a step from the beginning towards here with the profiles, but it really, at the end, we really need to only change these profiles, and the calculation is done in the background. Yeah, and then all these values are just placed inside of the simulation. We have here our attractivity, we have a profile distribution which states what kind of function is on which plot. So we need to know, okay, for example, here's the first profile distribution, assigns the most attractive plot to a function. I think it's just a value of 1 somewhere. Yeah, there will be a 1 in it. So it assigns the first residential, commercial and industry somewhere. And then with the attractivity we can measure our the attractivity of each plot. It's a matter of, so as stated up here, like we have our attractivity. Yeah, store is a good name, from profile to parcel, and we go through all of them and multiply it with the current distribution of profiles on them, and with this we get at the end, like it's actually rather, it is actually quite simple calculation, because we just add here every time the attractivity times distribution to our current attractivity. It's simple mathematics, but we just need to loop through all of these values. Yeah, and then we can add it to, like this is just normalizing this here with minimum and maximum attractivity. So we have like a range from 0 to 1 for the attractivity. And know then which parcel is most attractive for a function. And then we have this for all land uses in this iteration, and assign this with this function. There's a certain random value included. I'm actually not sure if it, yeah, down here it's used. Yes. Just goes through the yeah, it's like a lottery wheel. It goes through the attractivity values, and with a certain random factor, like it gives those plots with a high attractivity the biggest space, and if our random number falls into this space, it will assign the land use function to it. And this is, it's doing it for yeah, the amount of population that we need, and then it will do the same again, as we saw before. It was like these charts, they were growing, the pie charts, and when the simulation finishes, it will give us some evaluation of it. So there is, on the one hand here, the gross area per person, net area per person, gross area per household, net area per household, this is the profile distribution on each plot. Here you see the current distribution of this is in consideration of the trips. We will have a look at this later. And then just visualization of the outcome. I think that's it for the explaining the algorithm at this point. Now let's go into customizing and then evaluating the algorithm. I hope this was clear enough, and have fun.